Hello. This is the introduction to section 7.2, optimizing using linear programming, the graphical method. Okay, so you may remember I talked about an example, a hypothetical situation where you're trying to save lives by loading a cargo plane with a certain number of bottles of water and medical kits. Say you're sending a plane load to a earthquake-torn region. Sorry about the plumbing noise. So I think we talked about these things a little bit, but just to be more specific. Okay, so this is all an example about how to take an actual application problem and turn it into a linear programming problem, and then solving it, at least in section 7.2, just using graphing in the plane, right? So anyway, so let's say that I'm going to start writing over here. Hope you guys can see that. I think you can. Let's see. So if, so if X is equal to the number of large water containers, and Y is equal to the number of medical kits, let's see, if we're talking about volume constraints versus weight constraints on these, the volume of the large water containers, water bottles, was 5 cubic feet, and the weight was 20 pounds. Each medical kit takes up 10 cubic feet and weighs 8 pounds. Kind of more like a medical tent. Let's get that off there. Okay. Alrighty, so let's see. So if that's how we designate X and Y, then, and we're assuming, assuming each bottle of H2O saves, let's see now, what was that idea? Oh yeah, saves 10 people for 3 days. So we're talking about sending the supplies that will help people get through the next 3 days, right? And that each medical kit, tent, whatever, each medical kit serves 5 people, saves. Okay, then the total number of lives saved would be equal to 10x plus 5y, right? Is total number of lives saved. All right, so that's turning the English into, this is called the objective function. Okay, and our objective is going to be to maximize the number of lives saved, right? Let's talk about these constraints. If the volume of each bottle of water is 5 cubic feet, then in total volumes will have 5x, 5 cubic feet per container multiplied by the number of containers is the total amount of cubic footage taken up by all the waters, to which we're going to add all the cubic footage taken up by the medical kits, which would be 10 cubic feet per medical kit. So yes, 10y. That's for volume. What about weight? What should I write there? Well, the weight of each large container of water is 20 pounds, so 20x is the total amount of weight taken up by water, added to which we get the total amount of weight taken up by the medical kits. That'll be 8y. All right, so what are the constraints of the plane? Let's assume that, so we're making an assumption here. So assuming volume on cargo plane has to be less than or equal to 40,000 cubic feet, and weight on the cargo plane has to be less than or equal to 40,000 pounds. That was actually the more accurate. 40,000 limit on the cargo plane, that was kind of just ballpark figure. You're going to see in the next example when we go on to section 7.4, when we talk about scaling this up for more than just two variables, that I got much more specific about these numbers. Okay, so those are our constraints, right? This all together gives us our constraints. So putting this all together, we're going to get the constraints on the situation, right? Otherwise, we would just save infinitely many lives, right? But we have some constraints, and they get expressed as inequalities. All right, so here we go. Here's how we formalize this in general. And you're going to see this pattern repeating in when we have more variables and more constraints in the linear programming section. So we formalize it this way. We say what our objective is. Our objective is to maximize the objective function. Which we've created to be equal to the number of lives saved. So we're going to maximize z equal to 10x plus 5y. Okay? Subject to these constraints. Here they come. We need 5x plus 10y to be less than or equal to, so that's the total amount of volume taken up, 40,000 cubic feet. We also need the total weight, 20x plus 8y, to be less than or equal to 40,000 pounds. So again, this one's in volume, this is volume in cubic feet, this one's weight, and it's in pounds. Right? And of course, we only want to talk about x and y greater than or equal to 0, right? Because we want to only talk about positive numbers of water containers and medical kits. Those can't be negative. They could be 0, though. All right. So, this is something you do in linear programming all the time. You state what your objective is, you state what the objective function is, and you state the constraints. Okay. Now, the way we're going to solve this is using the graphical method. Okay, so that's basically posing the question. Okay, so solving by using the graphical method. And that's really only possible for us humans when there's only two inequalities and two unknowns. If we try to do it graphing in 3 space, it gets too ugly to be any help. That's why linear programming, the simplex method that's coming up later in chapter 7, that's why it was invented. Okay, so, but let's solve this one. So, you've been graphing inequalities for a while. You've been graphing feasibility regions for a while. That's what we're going to do right now really quickly. So if you need to revise about how to do that, how to graph that system of inequalities and get a region, go back to that part. That was from before spring break. So our feasibility region is going to give us something like this. The constraint on volume here. You can see that there's some points that would be on the boundary line of that. Those points were, let's see, 8,000, 0, right? 8 times 5 gives you 40, and also on that one would be 0, 4,000. Because 4,000 times 10 gives you 40,000. Right? So we had that line there. That's for the volume. So that gives us something like this. Okay. And so let's see, this is about the volume. And of course, that's a less than or equal to, so that tells us give me everything below this line. But of course, these two constraints tell me give me everything in the first quadrant. So just thinking about volume, we're down to this triangle. Let me just put this marking here. This is 8,000, 0. We need the corner points, right? And this might be one. And this one is 0, 4,000. Right there. Okay. All right, so that's for volume. I should have done that in a different color. Let's do the weight. That one there, can you graph that? You want to stop the video, you do that yourself. Come back and check that for the weight, we're looking at something that has points like 2,000. That marker. On the weight, we should have things like, 2,000, 0. And 0, 5,000. Right, so those are points on the boundary of that half point. So that would give us 0, 5,000 there. And 2,000. Let's see, that's right about there. 2,000, 0 there. So these are the weight constraints. The boundary of it, right? So that's weight. But again, this is a half plane, everything below that blue line. All right, so what's below both the blue line and the black line? It's the red region, the feasibility region. And so that's going to be in here. So lo and behold, if we, so we're looking at this feasibility region. So the feasibility region, no longer with that marker. Feasibility region has a corner point we need to find, right? How do we do that? How do we find where two lines intersect really quickly? We run off and use our REF, right? So we use the equation of this line in black, the volume line, which is just take the equality on that inequality. That's an equation of a line. We take the blue line here. We end up looking at finding that point of intersection. That point right there, we find it by running with our REF on 5, 10, 40,000, and 28, and 40,000. If you run that through our REF comes back with that this 1001, and coordinates at that point are 500 and 3750. So that tells us the coordinates at that point right there. 500, comma, 3750. That's where those two lines intersect. Of course, this is another corner point of our feasibility region, 0, 0. But the good news is the feasibility region is bounded. Bounded. Why is that good news? Because you're supposed to be thinking about the corner point theorem. Corner point theorem says if your feasibility region is bounded, so enclose it in a circle, think of it that way, then you can solve any optimization problem. Therefore, we can find a maximum z-value, and that maximum is going to have to occur at one of these corner points. So we only have to look at the corner points. But you have to write stuff to say this. So since the hypotheses or the premise of the corner point theorem is satisfied, a maximum z, which remember here now, we're starting to think about the problem again. That's the number of lives. A maximum number of lives saved is possible to find. Is found at one of the corner points. One of the vertices of our feasibility region, polygonal feasibility region. So now we make a corner point table. So you need the x and y coordinates of each one of your corner points. There are 4 of them here. Now you need to think about what we're maximizing. We are going to be maximizing z, which is equal to 10x plus 5y. So we really need a 10x column, and we need a 5y column. Okay. So now you just list the corner points, which are 0, 0. Probably not going to be much help. That means we're packing 0 waters and 0 medical kits. What's this corner point? 0, 4,000. This one here, 500, the one we just found using our REF, 537.50, and 2,000, 0. Okay, so now we just need to multiply all the x coordinates by 10, 0, 0, that's easy. 10 times that gives us another 0. Excuse the rustling of the kid in the kitchen. 10 times 2,000 is 20,000. Right? Can you guys see this? Let's see if I can make that better. Okay, and now 5 times y. So look at all the y coordinates, multiply them times 5. So again, we get 0. 5 times 4,000 is 20,000. 5 times 3750. I've got that here somewhere. Let's see. 5 times 3750 is 18,750. You would multiply that out, right? And then what happens here? 5 times 0, that's 0. So, total number of lives saved under each of these packing plans at the corners, one of which is going to be our maximum by the theorem. Lives saved under this plan, where you put nothing in there, well, no lives saved. If you put in, what does this represent? All Y, all medical kits, you're going to save 20,000 people for 3 days. What happens here? This adds up to 23,750. More lives saved. This one, only 20,000. So notice if you just send all water, you save 20,000 lives. If you send all medical kits, it turns out you save the same number of lives. So a combination of the two of them, this extra point we went to the effort to find, gives us maximum number of lives saved. So maximum lives saved. This is, you write it, that sentence at the end. So when how many bottles of water are packing 5,000 water bottles. And let's see, how many medical kits? 500 water bottles. That's the X, 500 water bottles, that's much more reasonable. And 3,750 medical kits. And now you're done.